In this 10-minute video, I would like to tell you about a project I am working on to improve heliostat tracking accuracy using a dithering feedback system. I will test this idea using a small-scale model of a solar thermal power plant. This system can be used to improve solar thermal plant performance and to reduce the cost of heliostats. This should significantly reduce the cost of electricity produced by these plants. The project has been supported by a grant from the California Energy Commission, and a patent application has been submitted. Large-scale solar thermal power plants, such as the one shown here, which is located in Barstow, California, employ thousands of heliostats, which are large mirrors attached to motorized mounts. They rotate throughout the day to keep their reflected sunbeams all focused on a single point. This point is called the receiver, which gets very hot from all the sunlight hitting it. Its heat can be used to make steam and electricity. It's very important that all the mirrors reflect their light accurately to the receiver. Otherwise, the receiver will not get sufficiently hot and the plant will lose efficiency. So, one of the key problems to be solved in these plants is how to align the thousands of heliostats. Given the known position of the sun and the position of the heliostat and that of the receiver, one can calculate the required mirror angle and command the heliostat to move to that angle. However, the heliostat may not be sufficiently accurate to move the mirror to the commanded position. In that case, the sunbeam may miss the receiver. My system is designed to provide feedback, which is able to determine if the sunbeam is missing the receiver. It does this by surrounding the receiver with light sensors called photodiodes, which are shown in this drawing as circles surrounding the rectangular receiver. These convert sunlight into electric current. If any of these are hit, that means that some sunlight is missing the target and one of the heliostats must be misaligned and needs adjustment. But the question is, which heliostat is the problem one? That's where the innovation of this project comes in. What happens is that each heliostat mirror is being caused to mechanically vibrate at a unique frequency. This is called dithering. The sunlight reflecting off that mirror is deviated or dithered very slightly at that same frequency. The photodiodes can detect the change in light intensity at this frequency. An analysis of the photodiode signal can find which frequencies are present and thus tell which heliostat is misaligned. An adjustment can then be applied to fix the misalignment. The system I've built to test this idea is a small-scale model of a solar thermal power plant. Let's take a look at each part of the system. I've used small mirrors mounted on commercial telescope mounts as my heliostats. The mounts can receive commands from a computer that tell them where to point the mirrors. They can also tell the computer the altitude and azimuth of the mirror. This communication is done via RS-232. On the back of each mirror is glued a small patch of piezoelectric material. There are two wires soldered to the patch that carry an electric signal on them at the desired frequency. The piezoelectric material converts this electrical signal to a mechanical vibration, which causes the mirror to vibrate slightly. The next part of the system is the target to which we are trying to direct all the sunlight and its associated electronics. The target is a photodiode array arranged in a diamond pattern. In a real power plant, there would be a thermal receiver in the center of the target. Each photodiode is mounted in a black cylinder with a small hole drilled in it to allow in the sunlight. The electrical signal from each of these photodiodes travels on a cable to the electronics. The electronics are all mounted in this rack. The photodiode signals go first to an amplifier module. This module takes a signal from each photodiode and amplifies the high-frequency component. The amplified signals are then digitized by a module in this chassis. This module is commercially available from National Instruments. Another module in this chassis is responsible for generating the dither signal that makes the mirrors vibrate. The dither signal is sent out to the heliostats on the gray cables. The gray cables also carry the RS-232 commands and power for the telescope mounts. The whole system is controlled by a laptop that performs the analysis of the photodiode signals, as well as calculating the necessary corrections for the mirror angles. Let's see the system in action. There are 4 heliostats in the system, each of which can be separately controlled to position its mirror at the desired altitude and azimuth. In this clip, sunbeams reflected from the 4 heliostats are being brought into the target region, based on a rough calibration of the mirror positions. However, the calibration is not sufficiently precise to bring the beams onto the target, which is the region between the 4 photodiodes. In this clip, which I have sped up for clarity, the feedback system is applying corrections to the mirror directions to bring all of the beams into the target region. Note how each beam is being independently brought towards the center of the photodiode array. It takes some time for the corrections to bring the beams into the target region, because the steps only happen every 15 seconds, and each step is rather small. Now, all 4 beam spots are in the correct position. Once the beams have been captured, they can be kept on target indefinitely. Here, I intentionally move one beam off target, and then watch the feedback system bring it back on. This shows a screen capture of the controlling computer. The diamond array of 4 dots represents the photodiodes. If any of the dots are red, that means that some light is striking the corresponding photodiode. The array of 4 outer dots next to each inner dot represents the 4 heliostats. If any of those dots are red, that means that light from the corresponding heliostat is striking that photodiode. Now let's turn the system on. The top and right-hand dots are red, indicating that sunlight is striking them. However, the dither signal has not yet been turned on, so none of the outer dots are red. Now, as I turn on the dither signal for each heliostat, some of the outer dots turn on and the misaligned heliostats can be identified. The system then calculates corrections to adjust those heliostats so that their reflected light moves towards the target. The 2 graphs on the bottom show Fourier transforms of the right-hand photodiode signal. The graph on the right shows the frequency range where the dither signals are located. One can see peaks appear at different frequencies as light from different heliostats strikes that photodiode. Watch as the system slowly reacts to each of the misaligned heliostats and eventually brings them all onto target. The corrections take some time to bring the beams onto the target, since each step is rather small. Finally, all the beams are on target, and the amount of light spilling is only a few %. As we've seen in this video, the small-scale model of the feedback system works well. It is able to control many heliostats simultaneously and to achieve tracking accuracy at the milliradian level. I have begun testing at larger scale and to investigate possible industrial partnerships. Thank you for your attention.